Well, hello, everyone. Thank you very much, Tom and Psychot, for inviting me to give an overview talk. It's a pleasure to be here. As Psychot said, the University of Oregon is one of the nodes or satellite nodes of the CQN, and we've been involved in it since the start. And we're very happy to be in the center. It's been a really great stimulus to our own research program, and lets us interact with some of the leaders in the world, really, in this field. So what I'm going to do today is provide a high-level overview of quantum information science. And then I'll also talk about some more detailed research topics that we're working on in our group. And I work with Professor Brian Smith at the University of Oregon. I'll also talk a little bit about where quantum is going in the commercial sector and what sort of inflection points to look for as that process goes forward. So with that, I will begin. First, I'd like to let this information leak out. This is the first time the world has been informed about this new journal that the Optica Publishing Group has decided to create a new journal in the area of quantum information science. And so I suggested it, and of course they said, well, you suggested it, so you have to be the editor. So they twisted my arm and I agreed to be the chief editor. So we're now recruiting associate editors to open up this journal. And I hope everybody will think about submitting a paper to this journal to kick it off in a very strong way. And of course, we're covering all the usual topics, but since it's the Optica, which is the former OSA, Optical Society of America, this journal will be focusing on optical implementations and optical aspects, both in fundamental science as well as engineering. So I think the work that you're doing here fits perfectly into this new journal. So please contact me about submitting a paper. Okay, as Psychot mentioned, Chris Monroe and I, about 6 years ago, wrote a proposal to the Congress, which was ultimately funded, called the National Quantum Initiative. And I should just again give a plug that this was supported, this lobbying effort was supported by the OSA, which is now the Optica. So they have quite a stake in this field because they recognize that optical engineering and science is the single most important enabling technology for quantum information science. Okay, so what do we say when we talk to Congress people and non-experts in this field to convince them that this is something new and interesting? Well, first we have to explain what the first quantum revolution was, which happened back in the 50s, 60s, and 70s. And this was based on the behavior of materials made up of many atoms, like a semiconductor diode, or a semiconductor transistor, or a laser, etc. This led to things like atomic clocks and the GPS system worldwide. But the second quantum revolution is based on the behavior of individual atoms and photons with entanglement between them. So engineering and controlling single atoms and photons in exquisite entangled quantum states is really a great challenge, especially over long distances. So we like to categorize the overall field in three pillars. The first is quantum computing and simulation. And this has a growing number of potentially useful applications. Of course, we don't have a quantum computer yet that's scalable and can solve the really big problems. But many companies are building small prototypes, and probably within 10 years, maybe we'll have something that's really scalable. And there are many problems, as I list here in that column, that can perhaps be accelerated by quantum computers. But I should point out that most problems in computer science cannot be accelerated by quantum computer. And there's a simple way to see that. The only problems that can be accelerated greatly are those that can be mapped onto the Schrodinger equation, which is the fundamental equation of motion of quantum mechanics. So things like word processing, graphical design, those things probably cannot be mapped onto quantum mechanics, so there's no speed up. However, for those problems like optimization that can be mapped, they're probabilistic endeavors, and quantum mechanics is also a probabilistic theory. And if you can map those on, then you can get speed ups that are, unimaginably large. Okay, the next pillar, of course, is quantum sensing, and we'd like to be able to sense and map magnetic fields, gravitational fields, and so on for biological imaging, GPS-free navigation, and other useful applications. And now here we get to quantum communication, which of course the CQN is pioneering research and development for that area. And we have this list of things like secure data encryption, remote quantum computing, distributed sensing, multi-party entangled protocols like voting security, and so on. So let's talk about those individually. The first one is quantum computing and simulation. Well, the platforms have to be physical objects. You cannot do computing of any sort unless you represent a bit with a physical object. So a classical bit is just represented by a light switch. It's either on or it's off, 1 or 0. A quantum bit or a qubit is in this very fuzzy, wavy, undetermined state that is, you cannot say that it's both on and off at the same time. You can also not say that it's neither on nor off. You just simply can't say. There's a potentiality that if you observe it, it will be either on or off. But prior to observing it, you cannot say anything except the quantum state, which is an abstract mathematical concept, which is very hard to describe to a congressperson. With 1 or 2 exceptions. Now, there are a number of platforms for representing a quantum bit, and I'll go through those very quickly. I took these pictures from an article in Optics and Photonics News, again published by Optica, OSA. And the first we have our spin qubits. So we know that an electron is a quantum object. It spins counterclockwise or clockwise around some particular chosen axis direction. And you can use these spins of electrons or nuclei that are trapped in a solid substrate, such as diamond, and you can manipulate these individual spins. And you have quantum bits because it's either spinning clockwise, that's a 0, or spinning counterclockwise, that's a 1. Other groups are working on fabricating nano devices, which are artificial quantum dots. So fabricated devices as opposed to nature-given spins of atoms. Okay, another one is called superconducting qubits. And this is think about a metal wire that's in the shape of a ring, and current can rotate around it or travel around it in a clockwise direction or in the counterclockwise direction. Those are 2 possibilities. But you can also make it into quantum superposition of both clockwise and counterclockwise. And this forms the qubit. Then you can measure it and determine which way it's traveling. This requires very low temperatures in order to have superconducting materials. So it's easy to make many of these devices because they're mass produced, but the quality is questionable. It's hard to make them identical. Another one is trapped ions and trapped neutral atoms. So an ion is simply an atom that's had 1 or 2 electrons removed. So you can then trap it with magnetic and electric fields. And you trap an array of these, maybe 30 of them, and you manipulate the quantum states of the electrons inside the ions or the atoms using lasers. And again, you can drive a quantum computer by bringing these atoms or ions nearby to each other and interacting them through laser fields, and then they can form some kind of a computer operation. And then you can read them out using lasers. Okay. Now, the benefit here is that all the atoms are identical and they're also fully connected because optics comes to the rescue. You're using lasers, therefore you can have one ion interact with the other ion either through laser fields or through simply the vibration of the chain. If you think about this chain of ions as a bunch of beads connected by springs, if you jiggle one, it jiggles all of them, and you can therefore transfer quantum information from one to the other. Okay, I know I'm going very fast just to give you this overview. And the final one is photonic circuits, where we try to do everything with light. And the upper box 4A talks about photons, which of course are individual excitations or particles of light. And one tries to control the states of these photons and interact them and do quantum computing. And the other one is called squeeze light, in which we don't talk about single photons, but we talk about fields, electromagnetic fields, or the fields of light, the states of light. And you can manipulate these field states as opposed to manipulating individual photons. And you can also carry out quantum computing operations. So all of these I just mentioned are being pursued by startup companies and by researchers at universities and government labs as well around the world. Okay, next one, platforms for quantum communication. So we have two people, Alice and Beth, and they wish to exchange quantum information represented here by a quantum wave function, psi. Well, how do they do that? They can't use tin cups and a string. That doesn't work because a string is a classical object, and you cannot transmit, especially at room temperature, a quantum state across a string. Now, if the string were very thin, made of like maybe a single strand of atoms connected together, and you cool them down near absolute zero, you actually could transmit vibrations through quantum channels. And people are studying optomechanics. In fact, here at the University of Arizona, there are people studying optomechanics. So that's kind of a joke, but let's now talk about different platforms. So you can do satellite to ground, and there's already been some space-based satellite demonstrations of quantum communication. You can also try to do satellite to satellite. And these are good because you don't have a lot of losses when the photons travel through the atmosphere. But the rate is very low because the beams tend to spread out quite a lot. So to increase the rates, you might want to use optical fiber down on the ground, as we do with the internet now. And you can have potentially high rate, but you have to build quantum repeaters because optical fibers are lossy. And even the scientists at the University of Arizona have not figured out how to make lossless optical fiber. So we have to have repeaters, which means you somehow measure them, you somehow relay the information in the quantum state without actually measuring it, because if you measure the quantum state before you repeat it, you actually destroy the quantum information. So it's a very big challenge, both in physics and engineering, how to build a quantum repeater. And that's one of the tasks that the CQN is working on quite hard. So let me show you a nice example here. This is just published very recently in Physical Review Letters, an example of entangling trapped ion qubits separated by a pretty large distance. So in this case, 230 meters. So the idea here in cartoon form is somebody, oh yeah, turn off your microphones. Quantum feedback. So the idea here is that we have our two parties, Alice and Beth, and they want to have some entangled states between the two. So what they do is they send out some quantum signal into a central station, and these two people I call Cora and Dora, and this is actually an excerpt from my quantum comic book, which I will talk about later in the talk. And they do some kind of physical operation which leads to entanglement between the particles that Alice and Beth retain in their laboratory. Well, how does that actually work? Well, Professor Tracy Northrup at Innsbruck University just published this paper in Physical Letters, and what they do is they have these two ions, one on the left, one on the right. A is Alice and B is Beth. And each of these ions is trapped between two mirrors, which is an optical cavity. Now they manipulate the state of these ions with laser pulses, and they force or they encourage the ion to emit a photon, a single photon. And the cavity mirrors increase the probability that the photon will be emitted into the direction of the optical fiber, which then is coupled efficiently. So the A photon travels 510 meters into the central location, and the B photon in this case travels 10 meters into the central location. Then there's some optics. Magic is all done with mirrors. There's a beam splitter, BS, and then there's some other beam splitters, PBS, and then there's these orange boxes, which are photon detectors. And depending on which of these photon detectors detects a photon, there's two photons, so there's different possibilities because there's 4 detectors. Depending on which 2 detectors register a photon count, that tells Alice and Beth what their entangled state is. So they don't know in advance what it will be, but once they learn which detectors clicked, then they are told your entangled state is such and such. It's called a Bell state, named after famous John Bell, which I'll mention later as well. So this is how it's all done. And it works quite nicely. They can entangle across their campus, these two ions. Again, it's just two atoms, which is pretty remarkable that you can actually control two atoms, keep them there, entangle them, store information, read them out, and do something. And if you can build an array of many atoms or ions, then you can do quantum computing. And this then allows you to connect two quantum computers that are in different buildings using a quantum network. Okay, there's some misconceptions that I've heard even some high-level government experts misspeak about. One is a qubit cannot really have two values at the same time. I mentioned that earlier. It's really just indeterminate until it's measured. But it's not the same as classical indeterminacy. It's not that the state has a certain value, you just don't know it until you measure it. It actually doesn't have any value. And when you measure it, the value emerges and it just happens. And that's actually a philosophical mystery, even to physicists. But it works, so we're going to build technology with it. Another one is that measuring, if you have two entangled particles, say Alice and Bet have their entangled particles, then when Alice measures her particle, she can determine the state of her particle. Now, it's often misstated that this somehow affects the state of the other particle. That's not true, because if that were true, then you could actually communicate faster than the speed of light, because that would be an instantaneous cause and effect. And if you believe, which all physicists do, that Einstein's theory of relativity is valid, then that's not possible. And in fact, quantum mechanics also tells you that that's not possible. So therefore, there's no faster than light communication. In fact, it's even worse, because a quantum network doesn't really give any significant speed up for classical digital communication either. It can give small speed ups, but it's almost not worth the overhead. So the real question is, if it doesn't give a speed up and it doesn't give instantaneous communication, then what is it good for? Well, it's only good for one thing. That's distributing quantum entanglement across very large distances. So perhaps only a quantum physicist or a quantum engineer would even care about that. So how do you convince funding agencies that this is an important thing? And I showed all the possible applications early in the talk, but of course, these are far into the future. So I like to say that right now, we're kind of in a similar position where the semiconductor computer industry was in the 1960s, just starting to build these systems. And of course, nobody could predict back in the 1960s that I would be talking on Zoom remotely, and other people would be watching around the country on their cell phones. Okay, now let's talk about platforms for quantum sensing. Well, quantum states of electrons and photons are extremely sensitive to external perturbations. This is both bad and good. The bad thing is that if you build a quantum computer with quantum bits, they're very sensitive. So any kind of thermal jittering or shaking or disruption, even from cosmic rays, will destroy the computation and give you a bad answer. In fact, some people think you have to put superconducting quantum computers underground to protect them from cosmic rays, which is a perturbation. On the other hand, it's a good thing because you can use this extreme sensitivity to build quantum sensors, which are exquisitely sensitive to measuring things like gravitational fields or magnetic fields. So here is a latest, greatest application I've been able to find as an example of quantum sensors. So this particular implementation is done at Nottingham University, and they built a wearable brain scanner. Now, brain scanning has been around for decades, but it's usually been quite insensitive, and they've been using so-called classical techniques measuring electromagnetic fields. But it turns out that using quantum sensors, you can increase the sensitivity by orders of magnitude. And this is greatly increasing the speed at which brain scientists and medical scientists can make discoveries. So how does this work? In this picture, this photograph, each of those little round objects there is one quantum sensor. They're all connected by optical fibers. And each sensor is, as they say in the caption, is as small as one Lego brick. And inside of that Lego brick is this complicated glass cell with metal wires forming magnetic shielding and magnetic fields, and then prisms and lasers and photodiodes and all that's stuck inside one little brick. That's an amazing piece of engineering. And then they have maybe 100 of these, and they put them in this plastic, looks like a 3D printed plastic helmet, and they can pipe out all the magnetic field measurements as the subject or the patient is told to do certain mental tasks, like think about a certain picture or something like that. So they're using this for medical research, things like autism and so on. Okay, now moving on to the next step. See, in the previous example, each sensor was operating independently and just sending a signal to the central computer where it was processed. But a very nice idea is to actually create sensors which are entangled. So if Alice, Bet, and Charlie have different, devices on their optical tables, and they can somehow pre-arrange that they're entangled, then when a signal comes in, turns out that the entanglement between the sensors increases the overall sensitivity. And it scales like 1 over m, where m is the number of sensors. And this particular example is actually taken from the University of Arizona, Professor Zheshun Zhang, where they set up a optical system and a radio frequency system to detect radio signals with very high sensitivity. Okay, next one. Tom Koch mentioned 100 years of quantum mechanics right now, but this is also 100 years of the invention of interferometric stellar imaging, which was done by the famous Michelson just over 100 years ago. And his setup is shown in the left, where you have stellar objects that send light down, and there are 2 telescopes. And each telescope has a lens, and it collects some light. And then it passes the light from each telescope, goes into a 50-50 beam splitter, BS, and then to two detectors. And then they have a device called phase, which is delta. And that's just simply a way to change the timing of one of the optical signals. So they bring these together and they interfere them. And of course, this looks like a Michelson interferometer. And 1 source, 2 slits, and then interference on a screen or on a detector. Now, if you change the distance between these telescopes, that number B right there called the baseline, and you continue to measure this interference pattern as you vary this baseline. So you have to put those telescopes on railroad tracks and move them around, or just wait until the Earth rotates and travels around the sun and they move and they spin and they change their relative orientation relative to the distant star. Lots of tricks you can do. But in 2007, John Monnier, who's a collaborator of ours, he's an astronomer at the University of Michigan. He used this kind of technique to make the first reconstructed image of a main sequence star other than the sun. And you can see the picture right there, where they map out the thermal temperature distribution of this star, Altair. Okay, now what does the actual apparatus look like? It actually looks like this. It's at Mount Wilson, California, and there's a central location, the dome there, and then they have these 6 outlying small telescopes. And then underground, there are optical channels, which are in vacuum tubes. So it's kind of like the LIGO system, where you have to connect all those different stations with vacuum tubes, and you send the light from each of those 6 stations into the central station, interfere them all, and then wait for this. You can't move those stations, so you wait for the Earth to rotate and move around the sun to get different parallax, you could say, onto the distant objects, and then you reconstruct as I showed. So that's the state of the art. They have 330 meter baseline distances. It's difficult to go beyond that because these vacuum tubes are very expensive. And in fact, if you tried to go 1,000 kilometers, they'd have to be curved, wouldn't they? So there's another alternative, which was carried out by Charles Townes, a Nobel Prize winner back in the 60s, 70s, and 80s, where he used so-called heterodyne detection. to do a similar thing. So instead of bringing the starlight together, what they did was they have a laser, which is a very stable single frequency laser, and they beam split it and they sent part of it to one telescope, interfered starlight. The other part, they sent that laser over to the other telescope and interfered those. And then they look at the optical signals hitting those four detectors. And then again, they have to vary the distance between the telescopes and they can reconstruct objects this way. So this eliminates the problem of having to send a very weak starlight from one telescope to the other. Now you have a very strong laser you can send across. And lasers are more robust against losses. So you could even use optical fibers to send the laser. And if you lose some of it, it doesn't matter, it's still a laser beam. The problem with the laser, though, is a laser has an undetermined number of photons in a given time interval or a given pulse. And that's a fundamental quantum property of laser light. In fact, I think Einstein, he didn't have a laser, but he was the first person to figure out a lot of these photon statistics. And a classical laser field, we call it classical, even though it comes from a laser, which is a quantum device. But laser light is the most classical of all possible light fields. And however, it suffers from the fact that the number of photons is not fixed, it's not determinate. It's actually like a superposition. You can't say how many photons are there until you measure it. So sometimes you get 10 photons, sometimes you get 13 photons, sometimes you get no photons. And so this is a form of noise which contaminates the signal you're trying to measure. And so this technique is not considered to be optimal. So another point there is the laser provides a time reference between the two telescopes. So I put two clocks there. Time for optics is very hard to measure because it's very precise because optical fields oscillate about 10 to the 15 times per second. And you have to have the timing better than that, maybe 10 times better than that. So you need very good timing references to do this. And at the current time, atomic clocks and a GPS system are not good enough to provide this timing reference. So you actually have to send this laser across optical fiber, which has to be path stabilized. So you know exactly what the relative phase is from one telescope to the other. So this system is limited by shot noise. That's the photon number noise in the laser. Okay, so now we get finally to the quantum enhanced version of this, which was proposed by Gottesman, Heterodyne, and Croak just over 10 years ago. But until recently, there haven't been experiments demonstrating this technique. So the idea here is instead of using a single laser, which puts out an unknown number of photons at a given time interval, you should build a device in the blue box at the bottom called a single photon source. And it puts out one photon at a time. And ideally, it can really put out exactly one photon every time you push a button. So this is called now a quantum state of light because it's one photon, one particle of light. So you take that one photon, which is shown in the red wave there, and you beam split it on a 50-50 beam splitter. And you send half of the photon to one side and half of the photon to the other side. Now, again, we're talking about superposition. You can't say that the one photon either went to the right or to the left. That's not good language. You also cannot say the photon went both ways, left and right. Then there would be two photons, but there's only one photon. So all you can say is this indeterminate. It's the quantum superposition state of the photon in the left and the right. What this means is that the state of the light in the two paths or the two beams is entangled. Even though there's only one photon, the light fields are entangled on the right and the left. So you take the light on the left, you send it through a free space or a fiber channel, and you let that interfere with the starlight at the left telescope. And then you take the half of the photon or the entangled photon path to the other telescope, let it interfere. Now the star is very weak. So actually the star in a given short time interval only emits one photon into the telescopes. So you're not actually interfering light, two photons from the star with this reference photon. There's one photon that comes from the star, and it could go into the left telescope or it could go into the right telescope. Now your single photon can also arrive either at the left telescope or the right telescope. And if you calculate all this in quantum mechanics, you get interference. So as you change this phase, this little blue box called delta, as you change the value of that phase, just like Michelson did in his old experiment, you see quantum interference. And the visibility of that interference depends on the separation between the two telescope sites. And I won't go into the details there, but they teach this in optics courses. So if you measure this visibility as you change the distance between the telescopes, again, you can reconstruct a stellar image. Now, the beauty of this, ideally, if it works, is that you eliminated the shot noise from the laser. There's no laser here anymore, just one photon. So you increase the signal to noise, which means you can detect much dimmer light from distant stars. However, you still have the problem, how do you get that single photon from one location to the other? If you go to an optical fiber, you have losses still, okay? And the other challenge is, for experts here, you need to have you need to control this quantum entanglement at the optical phase level in optical frequencies. So you need essentially a clock. Okay, but the loss in these channels, you have optical fibers, you always have loss. And so this again limits how far you can separate the two telescopes, because the photon will be lost as it goes to the other telescope. However, the advantage of this, which I kind of forgot to say at the start, is that the larger you can make the separation between telescopes, the higher angular resolution you can obtain in looking at a distant object. That's the purpose of all this. That's why they were able to reconstruct the surface of that star Altair by having a 300-meter separation. But if you want to image something like a black hole, which is angularly much smaller, you need to have a much larger telescope separation. But then you run into this loss problem. The single photon is lost, or you have a laser which has shot noise. So this proposal by Gottesman is the following. You put a quantum internet in there with the phase reference. And then ideally, you can transmit that 1/2 of the photon path coherently and quantum mechanically across the network with many repeaters, and you can beat the losses that you would normally obtain with an optical fiber. So this is an extremely challenging application, but it's a good motivator for people to build a quantum network. It's like a target that we have to figure out, what do we really need? We just need a chain of quantum repeaters to make this work. But there's a lot of development. This, I think, is like the LIGO project, which took 40 years to implement. This project will probably take 30 years out from now to implement this. But we're working on this. Okay, how to create these single photon states. So I'll speed up a little bit here. I know I'm going slow. Matt Brown, a PhD student in our group at Oregon, has done the following experiment, which I'll rush through quickly. You have a pulse laser at the bottom, puts out a pulse, you put it through a crystal, that spits out 2 photons. You detect one of the photons at the bottom called a herald, and that tells you, aha, I have 1 red photon now. So we have 1 photon. We go for beam splitters, we go to 2 telescopes. Our telescopes are very simple. We don't have lenses, we just have bare optical fiber. So our telescope aperture is 5 microns, pretty small. So it doesn't have any capability to resolve anything. However, if we have 2 optical fibers and we scan them, the separation between them, we can reconstruct the shape of the source object, which is an incoherent source, which we mocked up in the lab. So the actual experiment is on a tabletop, looks like this. I just go through it really quickly. We have a laser on the far left, sends out pulses. We split it. We use 1/2 of that up onto the thing at the top called a rotating diffuser, that green rotating disc. It has a mask of some sort, making some kind of incoherent object. Then we take the bottom part, we go through frequency doubling and down conversion crystals and heralding detection to make our single photon reference. Then we have our single fibers, we move them around. We look at interference using the FBS, which is fiber beam splitter. We count photons. We change the distance between the 2 fiber tips, which are our 2 telescopes, and we try to reconstruct something. And it works. So on the left is the visibility of the interference pattern as a function of the telescope separation, which is the distance between the 2 fiber tips. And you see this nice oscillation. If you Fourier transform that, you create the function on the right, which turns out in this case to be the auto convolution of the source with itself. I won't go into details about that, but we can talk later if you wish about that. But anyway, this works perfectly at the level that we're doing this. It reconstructs the object perfectly. And we're using entangled photon paths to do so. Okay, now moving along quickly here. This is supposed to be a high-level talk. So let's talk about something in the news. This is a news announcement from IonQ, and I believe we'll have a talk from Jungsang Kim following this talk from IonQ. And they have recently teamed up with Hyundai Auto Company to use quantum computing to advance next generation batteries. And this, to me, sounds challenging because we don't really have a fully functioning quantum computer. So they must be developing what I would call toy models, where they're trying to map the actual chemistry onto a simpler problem. They can map that onto their Schrodinger equation. They can program that onto their trapped ions, and they can compute some kind of results. So this I would call research, and Jungsang can tell us, well, if he's allowed to, how much progress they're making in that direction and how many years it might be until we have an actual battery that's been improved by using quantum computation for the design process. Okay. So this diagram is from a workshop report that I recently helped organize and write. It was funded by the National Science Foundation, and I believe we have one or two folks from NSF on the call here. Thank you, NSF, for sponsoring this workshop and many other workshops in the past, which has really led to the explosion of funded research in quantum information science in the United States. So this diagram shows what we conceive as the progress that's needed to go from basic science conception on the left to commercial development on the far right. And in the middle, you have this little loop we call the scaling loop. So once you have a proof of concept demo, like we have for the quantum telescope, that's the easy part. That's just quantum optics. Now you have to go into this loop of scaling. Now, scaling means you need to make it work with more components over longer distances for longer times with more qubits. And scaling is a mathematical terminology, but just think of it as making everything bigger. Then you can also have application demos, like maybe this battery research. You need to have a target application you're working towards. You can't just say, I want to build a quantum computer, but I don't know what it's going to do, or a quantum sensor, or a quantum communication network. So in our case, we're proposing the Entangled telescope project as a target, application target for quantum communications. And then you have to demonstrate somehow. Number 6 is called increasing quantum advantage. So quantum advantage, there's 2 kinds of quantum advantage that we wrote in this report. One is you can take a known task and do it faster and better and more precise. That's what quantum computers do. But the quantum telescope is of a different nature. It actually enables you to do something you simply could not do with classical technology. It's not making it faster or better, it's actually doing it the first time. So quantum telescope over, thousands of kilometers would be a new thing. Okay, then you have to go into full stack integration, user access, scientific applications, commercial development, and so on. Now, this, we have to learn from history. And this was the dot-com bubble back in the year 2000, and it blew up and then it blew apart. And the VC deals, venture capitalist deals, blew up and then they shrunk and eventually reached a kind of a steady state. And we now have what we have. So a lot of companies were grown and died. Well, we can expect a similar thing in quantum technology. This is a chart that I took from a website showing from 2019 up to 2022, the VC deals that were done in hundreds of millions of dollars. And you can see there was a huge growth just in the past 3 years, but then the first quarter of 2022, where this chart ends, would drop down. I don't know what happened in the past 2 quarters after that. But it's pretty volatile. There's been a lot of money put into it, and we don't know if this is the end of the boom or just the middle of the boom. Okay. Finally, inflection points to watch for. In quantum computing, we need error correction because qubits are very sensitive to errors and external noises. And so there's a thing called error correction. You can take a 100 or 1,000 qubits and use them collectively to represent 1 qubit. and then you can actually do error correction and defeat these errors. But that means you need a quantum computer that's 100 or 1,000 times larger than you would need if every qubit were perfect, which they never are going to be. So you might need millions of physical qubits to make a working computer that can do an arbitrary job. In quantum communication, we need a network and we need repeaters to make the network. They must be able to teleport a quantum bit without measuring or changing it. We need quantum memories, and we also need small quantum processors to orchestrate all the network operations. And finally, in quantum sensing, there are three types. I talked about them. There's individual ones like the brain scan. There's small area arrays like the radio receivers, and there's wide area arrays like the quantum telescope. So those are inflection points. If we see some of these start to happen, we know we're going to be in good shape. Okay, but now, finally, how to increase awareness of QIST, quantum information science and technology. There's certainly a shortage of trained scientists working in this field. So NSF and other places have been working hard to try to increase the awareness. So one thing I've done recently is I wrote a comic book. And this is the comic book right here. And you can all take a look at it. I have one copy of it here. It's 16 pages. And it's called The Bell Game. And it has to do with measuring entangled particles. And so it's written at a level for either congresspersons or high school students. Ideally, I think the high school students might be more interested. But that's the cover right there. And it was funded by a program at the University of Oregon. It came from the National Science Foundation called the Science and Comics Fellowship Program. And we wrote the comic last summer before the Nobel Prize was given. It turned out the Nobel Prize was given a few months later for exactly the topic that we wrote a comic book on. But we don't claim any credit for that. But on the back page, we increased awareness, although we hadn't published it yet. So on the back page, we did some art and some quotations of the three Nobel laureates from Stockholm, John Clauser, Anton Zeilinger, and Alain Aspect. And they did experiments from the 1970s up through the 2000s, verifying that quantum entanglement is a real thing, is a real aspect of nature. And that is what drives all of quantum information technology. So they finally, after many decades, were recognized with this Nobel Prize. And so we thought we would honor them by focusing this comic book and publishing this. We hope to publish it maybe through CQN. Okay, so finally, thank you very much. The group leader of all of our efforts at Oregon is Brian Smith, professor. And here are some of the students and postdocs who are working on projects. And of course, we're always looking for postdocs and students. So if you know people who might like to move to Eugene, Oregon, please let me know. Thank you.